These are the Lesson 9.3 notes on rational functions. Today we're going to look at what graphs of rational functions look like. We're going to talk about the vertical asymptotes and the x and y-intercepts on rational functions. First of all, what is a rational function? A rational function is basically an equation where we have a fraction with a numerator and denominator. And the numerator and denominator are made up of polynomial expressions. So we'll typically see lots of x's, or sometimes it'll just be a number in either the numerator or the denominator. All of our graphs today will have a horizontal asymptote at y equals 0. That's also known as your x-axis. We will eventually be working with rational functions that have horizontal asymptotes at other places. But for right now, all of these graphs today will have a horizontal asymptote there. For example, we're going to take a look at two equations to start off with. Both of these are rational functions. We have polynomial expressions in both the numerator and denominator. And in cases where we have multiple expressions, what we're going to do as we type this in our calculator is put an additional set of parentheses any place where we have multiple factors in the denominator. So you'll notice we have that here and here. If we had multiple factors in the numerator, we would do the same thing, but we don't have that in either of these cases. Let's take a look at our first equation, y equals 1 over the quantity x minus 2 times the quantity x plus 3. In our calculator, we're going to go to the y equals menu. We're going to type in 1 divided by two sets of parentheses. The first embedded set will have x minus 2, and we'll follow that off with x plus 3. And we'll take a look at what this equation looks like. I'm using a standard viewing window from -10 to 10 here. On my calculator, I'm not really seeing a whole lot. You can kind of see parts of a curve right here, but it's really hard to interpret what's going on here. I'm going to shrink my window down a little bit. I'm going to go in my x-min from -5 and my x-max to +5. And when we graph this, we can see a little bit more information that's going on here. Now, some calculators, you're not going to see some of this detail that's here and here, sort of these blips that look kind of like a heart monitor almost. What I want to draw your attention to are a couple of things going on here. You can see kind of a little part of a curve right here. On the middle of the graph, you can see kind of a curve right in this area, and then we see another curve here. These blips appear on some calculators. On newer models, you typically won't see that. Your calculator is actually showing asymptotes at those locations, and you may recall that when we're working with things like x minus 2 or x plus 3 in the bottom of this fraction, we don't want x to equal 2 because you'd end up with a 0 right here, and 0 times anything is 0. We can't divide by 0. So on our graph at 2, we actually have a vertical asymptote. We're going to denote that by a dashed line. For x plus 3, we wouldn't want x to equal -3. That would generate a 0 in the denominator. And on the graph that you see on my calculator, you'll notice at -3, there appears to be possibly a vertical asymptote there, and in fact there is. What the graph is actually doing is on the left side, you can see a little piece of a curve right here. Our graph is actually doing this. You can see the branch of a graph here. You can see kind of pieces of a branch right here. And you can see pieces of a branch in the upper right corner as well. This graph has two vertical asymptotes. They're located at x equals -3 and x equals 2. These are due in part to the factors that you see in the denominator, x minus 2 and x plus 3. They generate these vertical asymptotes, x equals 2, x equals -3. They're the values that would cause each of these factors to equal 0. This graph does not appear to have any x-intercepts. There is a y-intercept, and if you're wondering where that location is, it appears to be right below the x-axis. What you can do is you can always plug in to find the y-intercept zeros for x, because the y-intercept is located where x equals 0. And if you plug in 0 for x here and 0 for x here, what you'll actually end up with is 1 over 0 minus 2, which is -2, times 0 plus 3, which is 3. If you multiply this out, you'll get 1 over negative 6, or negative 1/6. So the y-intercept is located at the point 0, comma, negative 1/6. That's like negative 0.16 repeating. On our second graph, we're going to take a look at y equals x minus 1 over x plus 2 times x minus 4. So I'm going to go back to my calculator. We'll clear out our original equation and we'll type in parentheses x minus 1 divided by, again, our two sets of parentheses, x plus 2, parentheses, x minus 4. And we'll close it off with two sets of parentheses. This graph has some similar pieces to the last graph we saw. We are going to have, again, some vertical asymptotes, and they're based on our denominator. What value for x here would cause this factor to equal 0? Well, negative 2. Negative 2 is an asymptote of our graph. And you should notice on your calculator that there appears to be a branch down here in the lower left corner, and then another branch which reappears kind of in the middle up here. So that seems like a logical place for an asymptote. We also appear to have an asymptote over here on the right side of our graph. It looks like it's at 4, and that would make sense because if we plugged 4 in for this x, we would get a 0. So we'll do a little vertical asymptote right here as well, denoted by a dashed vertical line. I can see a branch down here in the lower left corner. I can see a branch up here in the upper right corner. We'll start with those two first. And then we seem to have a branch that kind of comes around and then down. If you're wondering, where does this graph cross the x-axis at? It looks like it could be anywhere between 0 and 2. This will be denoted by our numerator. Think of what would we have to plug in for x to get 0, because what we want is an x-intercept occurs where our y-coordinate is 0. So what would cause this numerator to be 0? Well, x equals 1 would be. If we plugged in 1 for x, we would get 0. 0 divided by anything is 0. So 1 comma 0 is our x-intercept. And our graph is going to come through here and crawl kind of through here. Now you might also be wondering, where's the y-intercept? We talked about that in the last problem. We'd find that by plugging in 0 for each of these x's. Now, something that's kind of neat is when you plug in 0 for each of these x's, you're basically left with the numbers in the problem, namely negative 1 in the numerator, and in the denominator, 2 times negative 4. If you crunch this out, you get negative 1 over negative 8. That's also equal to 1/8, or approximately 0.125. So just above the x-axis again. And our graph is going to kind of come down here, through the y-intercept, through the x-intercept, and down like so. The vertical asymptotes again are x equals negative 2 and x equals 4. We do have an x-intercept this time. It's located at 1 comma 0. And the y-intercept is located at 0 comma 1/8. If you want to use the decimal equivalent, that's fine. So again, let's review how to find these various parts of our rational functions. In our next problem, we have y equals 2x over x minus 1 squared. I want to get an idea or a picture of what this graph should look like. So we're going to type this in my numerator. You can just type in 2x. In my denominator, we do have parentheses x minus 1 squared. When we hit graph, you can see various parts of the graph. This one looks kind of interesting. First of all, remember that vertical asymptotes are based on what you see in the denominator. What's going to cause your denominator to equal 0? Well, x equals 1 would be something that would cause our denominator to equal 0. So we're going to do our vertical asymptote here at x equals 1. And I'll denote that on our diagram as well. You can see that's the case on our graph. The graph doesn't seem to have anything going on at 1, and the graph kind of appears to jump somewhere in here. X-intercepts are based on the numerator. What would cause your numerator to equal 0? Well, obviously here, if you plug in 0 for x, you would get 0. So 0 is your x-intercept. Your y-intercept is based on what happens when you plug in 0 for each of these x's. Now in this problem, if you plug in 0 obviously into the numerator, you're going to get 2 times 0, which is 0. In the denominator, you're going to get 0 minus 1 squared. That's negative 1 squared, which equals 1. 0 divided by anything is equal to 0. So your y-intercept is obviously also 0, 0. So what's going on with the graph? You can kind of see down here our graph is actually below the x-axis. It kind of dips a little bit, crosses at 0, 0, and comes up like this. So this graph is sort of interesting. It's really close to the x-axis. And then to kind of exaggerate, it kind of dips down, comes back up, and goes up like this. On the other side, you can see that it kind of starts here. It's going to come back along like this. There's your graph of that rational function. Our last one doesn't have as many parts. It's a much simpler looking equation. We're going to do 4 divided by, I'm going to do parentheses, x minus 3, because we're adding or subtracting in the denominator. So we are going to want to put parentheses around this if we type this into your calculator. Here's our graph of this function. Again, on some calculators, you're not going to see this vertical piece right here. On my calculator, it's kind of a giveaway that that's an asymptote, but that makes sense. That's what's going to cause our denominator to equal 0. So we do have our vertical asymptote here at x equals 3, which we'll denote with our dashed line. X-intercepts are based on what would cause the numerator to equal 0. There's no x in the numerator. There's just a 4. And similar to our first example where there was just a 1 here, if you don't have any x's in the numerator, then you're not going to have any x-intercepts. So this graph does not have an x-intercept. The y-intercept is what you get when you plug in 0 for x. When you do that here, you're going to get 4 in the numerator over negative 3. Negative 4/3 is your y-intercept. That's also known as negative 1.3 repeating. So that would be, if we did tick marks, about here. You can see in the graph starts below the x-axis, crosses the y-axis at 0, negative 4/3, and dips down. So we'll show that on our graph as well. And then over here, the graph pops up over here just to the other side of the asymptote and is going to hang out over by the x-axis on the right side. And there's your graph of that rational function. So to recap what we've learned today, there are basically 3 components to your graph that you should be able to determine based on the equation of the function you're working with. First of all, vertical asymptotes. Those are based on what you see in the denominator of your fractions. If we go back to our last problem, vertical asymptotes were located at 1 on this graph because if you plug in 1 for x here, that would cause your denominator to equal 0. So we'll identify our vertical asymptotes by what causes the denominator to equal 0. The x-intercepts of your graph are values that would cause your numerator to equal 0. So again, in the previous example that we looked at here, if we plug in 0 for x, we end up with 0 in the numerator. If you look at some of our first examples, up here, what would cause this x to equal 0? Well, plugging in 1 for x, so 1 was your x-intercept. So similar to finding vertical asymptotes, we find x-intercepts by figuring out what values for x cause the numerator to equal 0. And finally, for the y-intercepts, we're going to substitute 0 into the equation for x, and we're going to figure out what we get when you plug in 0 for x. You can see in some of the previous examples, we'll take the first example, if you plug in 0 for each of these x's, we get negative 2 and 3, which would give us negative 6. 1 over negative 6 was your y-intercept. So we find our y-intercepts by substituting 0 for x. A rational function may have just a single vertical asymptote or it could have multiple asymptotes. There could be also singular x-intercepts or multiple, but there will only be one y-intercept in your rational function.